Hello, this is Babu Dan. Welcome to the second day of the oxygen therapy seminar for biomedical technicians at Arusha Technical College. This day we are devoting to oxygen concentrators and analyzers. One of the big advantages of portable oxygen concentrators is that they can provide a nearly unlimited supply of oxygen as long as they're reliable power, even at home. In the event the power is not reliable, it is possible to have a portable O2 cylinder station which will fill a portable cylinder as a backup. However, oxygen concentrators are not limited to small portable home care units. There are in fact commercial industrial sized units which can supply an entire hospital. One alternative to oxygen concentrators is either on-site or off-site cryogenic liquid oxygen distillation plants. These can be very expensive. Many times hospitals will depend upon tanker trucks delivering liquid O2 and keeping the liquid O2 in a cryogenic facility rather than distilling it themselves. The advantage of liquid oxygen is a much higher capacity, certainly, for oxygen, but also it is pure 100% oxygen. It has removed the minor contaminants that are present in an oxygen concentrator output, namely argon and trace gases. Oxygen is vital in respiration, but it can also be toxic. Normal air is 21% oxygen, 78% nitrogen, and 1% trace gases, mostly argon. Supplemental oxygen, administered through a nasal cannula, for instance, increases inhaled oxygen and typically is kept to a mix not exceeding 50%. Breathing 100% oxygen for extended time can be toxic. Oxygen concentrators remove the nitrogen to produce 90 to 95% O2. They can never produce 100% because they are not capable of removing the 1% trace gases, including argon. Oxygen distillers remove all gases to produce 100% liquid oxygen. Both provide supplemental O2 mixed with air to 50% inhaled O2. O2 flow rate is adjusted to bring the SpO2 blood levels to greater than 95% in a typical therapeutic application. Pressure swing absorption is a concept used in an oxygen concentrator to remove nitrogen and pass oxygen and the 1% other gases. Zeolite acts as a molecular sieve to trap the nitrogen, which is a larger molecule, and it passes the oxygen and the argon, which are smaller. The final product remains the same ratio of 1% to 21% argon and other gases to oxygen. And therefore, the final product will be 95% oxygen and less than 5% other gases, mostly argon. Before we discuss the mechanism of pressure swing absorption and how oxygen concentrators are used for supplemental oxygen and for oxygen delivered through a ventilator, we'd like you to get together in small groups of 2 or 3 and see just how much you can teach each other. You are professionals. Many of you may know already much more about oxygen concentrators than your instructor. This will give you a chance to show your knowledge. Answer these 7 questions in your small group and then elect someone from your group to report your results to the class. So here's a very simplified block diagram of a pressure swing absorption or PSA concentrator. It shows the two zeolite sieve beds which are capable of trapping nitrogen while passing oxygen and argon. The reason there are two is that you have to be able to trap nitrogen in one and then switch the other one, and you see the release valves on both sieve beds. You have to be able to flush the nitrogen out because it eventually will just saturate the entire sieve bed. So that's the requirement for switching from one tank to the other, back and forth, as each becomes saturated. There typically is actually a third tank, which is used as a storage tank. This shows the output going directly into a flow meter and then to the patient. Typically, the valve will actually direct the air into a storage tank. So you'll see usually a bundle of 3 tanks. So this block diagram shows the PSA concentrator saturation sequence. So on the left side you see the block diagram with the nitrogen starting to get trapped, passing the oxygen and the argon out to the flow meter. Then as the nitrogen continues to accumulate in the left tank, you see on the right side that the left tank is getting saturated with nitrogen, and something has to be done about that or it will stop working. So the flush sequence is what comes next. Here we have 2 block diagrams showing the sieve swapping nitrogen flush sequence. If you look at the block diagram on the left, you'll see the left cylinder is saturated with nitrogen. It has been disconnected by way of the 4-way solenoid from the compressor output and from the oxygen output, and instead the 4-way solenoid valve has routed the compressor output to the right tank, and the output of the right tank is being directed to the flow meter as output oxygen. In the meantime, the release valve is flushing the left tank of nitrogen. Now this continues until, moving over to the block diagram on the right, we see that now the right tank is saturated with nitrogen. It has been disconnected by the solenoid valve, which has switched the compressor output back to the left tank, the now flushed left tank, which is capable of trapping nitrogen, and the output from the left tank is now being routed as oxygen to the flow meter. The right tank is now being flushed of nitrogen. Now, as I mentioned before, typically there is a third tank, an oxygen accumulator tank, so that instead of going directly to the flow meter, the output from the solenoid valve will go to a holding tank for oxygen. This acts similar to an electrical capacitor to buffer the oxygen and present a more uniform flow of oxygen to the patient rather than pulsed. Takes out the switching transients. Okay, once again, we're going to give you an opportunity in small groups to teach each other and find out just how much group knowledge this class has. And once you've answered these six questions in your group, pick someone in your group, a different person, to share your results with the class. All right, so the block diagram gave us a simplified understanding of the process and the sieve swapping, but it didn't go into all the details that are involved in the system. Now here we have a pneumatic schematic of what's actually going on in the system. It has more detail. For instance, you see the compressor goes into a heat exchanger. Then it goes into an air reservoir so that the air coming from the compressor is not pulsed. It's also filtered. Remember, think of any air reservoir as an electrical capacitor. What it does is it damps down any kinds of transient behavior. So coming out of the air reservoir, you have a nice smooth flow. Again, it goes into the four-way switching valve, but you also see that the exhaust valve connections are shown at the top, and you also see that the expansion chamber is part of the exhaust process, and so is the muffler. Now here you see the product storage vessel, as we described before, is actually the oxygen cylinder, the one I mentioned before, which acts as a buffer. So, and there are additional switches, check valves, and other precautions that you would expect in a complicated system. So let's discuss the major characteristics of the major elements in the system and also what service considerations apply to each. Now the compressor has got to be oil free and completely free of contaminant injection into the seedbed. If you get any kind of oil or any other kind of dust or other kinds of contaminants in the seedbed, it will quickly block it and destroy it. So the intake and output filters on the compressor have to be extremely clean and effective. You have to clean the intake or replace the intake filters on a regular basis. You also have to be concerned about moisture entering the seed beds. Moisture will cause the seed beds to swell and potentially block gas flow. Now, fortunately, the four-way valves are normally closed, meaning that if you lose power, the pathway to the outside ambient air is shut off. And that's good because if you're in a very moist or humid environment, Tonga for instance, or Dar es Salaam, you could have moisture seeping into the seed beds, clogging them, and then your concentrator no longer works. When it gets to the point where they're totally blocked, you pretty much have to replace the seed beds. Even though there should not be moisture penetration in an unused concentrator, it is very prudent to run unused concentrators at least weekly to remove the moisture. You never know how effective the valves are at sealing humidity out of the system. So a concentrator will clear itself of ambient humidity if the ambient humidity is under 90%. Now, one of the things is that only O2 analyzers can reliably determine the percent oxygen output, and that's certainly the primary consideration of measuring whether or not an oxygen concentrator is suited for service. Many concentrators have their own O2 sensor that will indicate low O2 or not ready if they detect that the output oxygen level is too low. Other things to consider are compressor service. There may be a need for valve cleaning or checking for piston head cracks, or it may be the compressor is not serviceable. It depends on the model. Other possible failures are things like solenoid valve sticking, defective solenoid opener shorted on the four-way solenoid or the exhaust solenoid. These are just some of the things that are possible. Okay, concentrator service tools and supplies. Well, of course, consult the service manual, the very first thing you do. But in general, you want hex wrenches, screwdriver sets, pliers, vice grip pliers, and possibly a strap wrench. You'll definitely want a multimeter, and certainly you'll want an oxygen concentrator analyzer with 3 functions. Percent O2 sensor, which should read at least 21% to 96% with plus or minus 1.5% reading accuracy and less than a 2-minute response. The concentrator analyzer should also have a flow meter that's 0 to 10 liters per minute at least. And a pressure meter is very useful from 0 to 200 kPa. And a concentrator output typically runs at 62 kPa. You'll want the manufacturer-approved filters for air intake and output. And you should have spare zeolite seed beds, fuses, wire nets, zip ties, other things for servicing the concentrator. All right, here's your opportunity for group problem solving, troubleshooting, using your collective knowledge. So once again, get into your groups of 2 or 3 people. Everything is self-explanatory on this slide. I need for you to answer questions 1 through 6. And once you have decided as a small group, answered those questions, we'll want you to present your findings by choosing someone to present your findings to the class at large. Now everyone's going to be doing this same problem, so you should be able to learn a lot from your colleagues. There's some very smart people in this room and very experienced. You're all my former students, so I know you're all super talented, and I expect you to do well on this. Well, this is self-explanatory. We'd like you to discuss the results as a class of what you found on the previous slide in small groups. And just for illustration here, we have 2 of the oxygen concentrator analyzer types that we have in the lab. The industry standard is the MaxTech UltraMax O2. That's the high-end one on the right, which ATC Lab has. And then, of course, you have the wind power units on the left, which are actually quite good in comparison at about 1/8 of the cost. All right, we have another group problem solving effort. We've hinted at a possible cause for this before, but we want you to get together in your small groups and complete questions 1 through 6. See what knowledge and what experience you can share in terms of what you think could be the cause and the solution. Okay, so discuss questions 1 through 6 as individual groups and then as a class. Here we illustrate the use of the pressure inlet on the wind power unit, which is on the left side. You'll of course have to choose pressure in the menu. And here I was using the wind power pressure inlet to measure ventilator breath pressure that peaked at 7 kPa, triggering the high pressure limit alarm. So it gave me a way of checking ventilator pressure alarm levels were okay. Okay, we have yet another group problem solving for groups of 2 to 3. In this case, it is a case of low oxygen saturation output. And again, work on the 6 questions as a small group, leverage your collective knowledge, and then present your results to the group at large and have a class discussion. Okay, let's present the results of the small groups on questions 1 through 6. Discuss the causes of low oxygen saturation and the dangers of unknown service history, and discuss the implications of low oxygen saturation for patient care in these cases. Let's discuss critical care applications for oxygen concentrators. Now, unlike bottled oxygen and piped hospital oxygen concentrators depend on power to operate. Their output is also not guaranteed, and they are Class 2 devices, which means Class 3 device is suitable for life support. So they are not FDA certified for life support. You need to have bottled oxygen available as a backup in the event that there is power failure. You also need to check them on a regular basis to ensure that they have at least 88% oxygen, pure oxygen content. So here's a summary of what we've covered so far. PSA oxygen concentrators can be a critical source of patient oxygen, used with either nasal cannula for supplemental oxygen only, or as an oxygen input to mechanical ventilator with a patient circuit in intubated patients. If used in this mode, you really need to have backup emergency oxygen tanks. Now, over 20,000 hours of operation is possible before replacing the zeolite canisters, but that requires frequent O2% calibration check. Excessive humidity can adversely affect zeolite lifetime, and moisture entering the zeolite canisters can swell the sieves and block airflow, which can be diagnosed by high pressure at the input to the sieve beds. Oxygen concentrators can take 2 to 20 minutes to reach peak percent oxygen output, and the O2 analyzer itself can take 2 to 3 minutes after connection to fully stabilize the percent O2 reading. Faults can include hose leaks, compressor valve leaks, O2 sensor aging, moisture, humidity damage to zeolite beds, which can recover, and there are, of course, the regular electrical failures as well. So our major hands-on exercise for this afternoon is going to be a complete calibration of your wind power unit at various levels of oxygen, ranging from 21% all the way up to 96%, using the available oxygen concentrators in combination with the LTV-950 ventilator, which will create an air-oxygen mix, which will allow you to achieve these intermediate values. Now, I've shown the configuration here of how the tubing is interconnected to the patient circuit, and that patient circuit has a standard connection to the ventilator. We will discuss later what the ventilator settings should be to, for instance, achieve an oxygen mixture of 40%, 60%, 26%, whatever. Okay, let's talk a little bit about the sensor that we're using to measure the oxygen concentrator output. Now, typically, the cheaper models of oxygen analyzers use electrochemical fuel cells or redox reaction sensors. The problem with these sensors is that they are actually decaying in the presence of oxygen. So the moment you start using them, is the moment they start dying. And they typically have a lifetime of only about 3 years. And even if you don't use them, their lifetime is not reliable beyond 3 years. Now, the electromechanical ultrasonic type has a lifetime which is indefinite, although it's guaranteed at least 5 years. It's because it uses the difference of speed of an ultrasonic pulse in two gases. Well, fortunately for our purposes, air is basically just two gases. 78% nitrogen and 21% oxygen, trace amounts of argon, but the argon does not significantly impact the mix of gas. So by using this technique, this concept that a pulse travels at different speeds in oxygen versus nitrogen, they're able to determine the ratio of oxygen versus nitrogen in the gas. And they can compensate out for the small amount of argon. Electro-optical, we know about the pulse oximeter. We've already discussed that, but that only measures the dissolved oxygen in blood. Of course, that is the most important measurement to the clinician, because when they're doing therapy by adding oxygen, ultimately what they're looking at is, did we get the pulse oximeter reading to go up to 95% or better? So that's the ultimate closed loop measurement. There is also electro-optical fluorescent, which is an expensive high-end product that can replace the electrochemical. It does have the advantage that, like electrochemical, it will measure oxygen in a multi-gas mixture, whereas the ultrasonic only measures in a two-gas mixture. So, for instance, you can't measure the oxygen in your breath with electromechanical ultrasonic sensor. You can't measure the oxygen in an anesthesia gas mixture because it has more than two gases. That's the drawback. The advantages are that it's not damaged by moisture, which the electrochemical ones can be. And it's ideally suited to oxygen concentrators and ventilators, which have only an air and oxygen mix. And it retains its calibration indefinitely, at least 5 years.